Okay, so the last practice problem we're going to look at this evening is going to be practice or problem number 19.6, and this is found on page 1362. So the problem over on the left-hand side, or the illustration, is a 20-pound block is initially held so that the vertical spring attached is shown as undeformed. Okay, so right now, before it's actually in position, or it's actually, we let the block hang, this is in its undeformed state. So it hasn't stretched out yet due to the weight of that block. Knowing that the block is suddenly released from rest, determine the amplitude and the frequency of the resulting motion and the maximum velocity and maximum acceleration of the block. Okay, so we'll go underneath and we'll get this one set up. Okay, so this is practice problem 19.6. Again, this is on page 1362. Now, we know that the weight of that block is equal to 20 pounds. Okay. The K factor for the one spring, so we don't have to do any equivalence, is 90 pounds per inch. I did do the conversion. That is equal to 1,080 pounds per foot. Okay, so multiplying by 12, right? Right. We want to find, okay, part A, the maximum amplitude, that's that distance from equilibrium, and the frequency. And B, we want to find the maximum velocity and the maximum acceleration. Okay. So we want to find XM. All right. Now, in this case, we look back. It said here that where it's at right now, this spring is undeformed. So what that means is if we kind of scooch back up and show you this illustration right here, it's sitting like this. They show the block on the end, but it said that it hasn't deformed the spring yet. So its natural equilibrium state would be here. But the problem says we're actually up here. So our amplitude is going to be the stretched state or the deformation that we see here. Okay, so because there is no extra force that is stretching it beyond its equilibrium point, our XM is going to be equal to that deformation, that natural deformation, when we actually let go and let that block stretch that spring. So we can find deformation through the spring rate. So K is going to be equal to P, which is going to be the weight of the spring, divided by deformation. So we can rearrange this to solve for the deformation. It's going to be equal to, our force is going to be the weight divided by that spring rate. Okay. So our weight, and that again, I just substituted instead of the force of P, I called it the weight because that's what's going to be pulling that spring down. So this is going to be 20 pounds divided by 1,080 pounds per foot. Okay. We're going to cancel out the pounds. All right. And then we are going to find our deformation. What do we get for our deformation? Josh got 0.0185, and that's going to be feet. Now, it's a small amount of feet, and we usually don't do that. Let's convert that to inches just to be more relatable. So I think we multiply by 12, right? So you should get the deformation also equal to 0.222 inches. And I think that might be what I reported, oopsie, on our last, all the way down to the bottom. Yeah, I did it in inches just because it's more relatable than such a small amount of feet, right? So 0.222 inches. Good. That matches what we got. So either one would work for a final answer. But again, sometimes depending on the units, sometimes inches in this case, I think is more relatable than the feet. All right, so that's the deformation. And we know that the deformation is going to be equal to that maximum amplitude. So 0.222 inches is going to be that value. Okay. All right, then we need to find the frequency. Okay, the frequency is going to be equal to, I remember, it's going to be the natural circular frequency divided by 2 pi. So we need to calculate that value there. And we know that value to be equal to the square root of our K factor divided by mass. Okay, so this is going to be equal to, we're going to use the 1080 pounds per foot, okay, divided by the mass. Now, we're given that block is 20 pounds. That is not mass. So we need to take the 20 and we need to divide it by 32.2, the rate of gravity, right? Like we've been doing throughout dynamics class. All right, so our natural circular frequency, what do we get? Hopefully 41.699. Okay. And then this is the number we'll use up here. So you should get 6.67 hertz or cycles per second. Okay. Any questions on first part? Got 2 more quantities to determine the velocity and the acceleration. Go ahead and calculate the velocities and the acceleration. Pull out your equation sheet if you need it. I'll do it on the side here. Good observation, Josh. But it comes out, doesn't it? Yes, notice that our acceleration 32.2, right? 32.168. Look at that. Yeah, and that makes sense because all we're doing is we're just dropping it, right? So it is going to have an acceleration equal to the rate of gravity in English terms. Okay. Any questions on 19.6? All right, I'm going to stop the recording here.